All around us, the world is in this constant state of change. Things are built up, they break down, they dissolve, they last forever. And while it might look like total chaos, it's actually all being run by a set of invisible rules. So today, we're going to pull back the curtain on the chemistry that makes the world work the way it does. I mean, really think about that for a second. You've got one metal that seems basically eternal, right? It stays beautiful and unchanged for generations. And then you have another that, if you just leave it out in the rain, slowly crumbles into reddish-brown dust. They're both metals. So what gives? And hey, here's another one for you. You stir a spoonful of salt into a glass of water, and poof, it's gone. But now, that same water can suddenly carry an electrical current. If you toss a piece of wood in there, though, it just floats. These aren't magic tricks, you guys. They're clues. Clues to how everything works. So, the solutions to both of these everyday puzzles? Well, they really come down to two fundamental ideas in chemistry: how reactive stuff is and how that stuff decides to bond together. Let's tackle reactivity first. Okay, first up, reactivity. The easiest way to think about this is that elements, especially the metals, have their own kind of social ladder, a chemical pecking order, if you will. Some are just desperate to get out there, interact, and cause a scene, while others, they are perfectly happy just being left alone. And this right here, this is our cheat sheet. It's called the Metal Reactivity Series. You see those elements way at the top of the stairs, like potassium? They are the life of the party, the most reactive. And as you walk down those stairs towards the bottom, where you'll find gold, they get more and more chill, more stable. This simple ranking is the key to our first mystery. Okay, let's break this down. At the absolute top of that staircase, you've got the wild ones, potassium and sodium. These guys react so intensely, sometimes even explosively, with something as simple as water. Then, somewhere in the middle, you find your everyday metals like iron and zinc. Now, they still want to react, but they take their time about it. That's the slow process we call rusting. And finally, way down at the bottom, you have the cool kids, the stable elites like silver and gold. They are so unreactive, they pretty much just ignore the world around them. And look, this is not just some fun fact for trivia night. This reactivity series is incredibly practical. We use it to figure out how to stop metals from corroding or how to get pure metals out of a chunk of rock. Scientists use it all the time to predict what's going to happen in a chemical reaction. This ladder has huge, real-world consequences. All right, so we've got it. Some elements are way more eager to react than others. That answers the if they'll react. But what about the how? When two elements finally do decide to get together, what does that relationship actually look like? And that brings us to chemical bonds. You can think of them a little bit like human relationships, honestly. They come in different styles. For our purposes, we can boil them down to two main types: a friendly partnership where everyone shares, or, well, a complete takeover where one atom is way more dominant. So first up, we have covalent bonds. Think of this as a true 50-50 partnership. Two atoms come together and they agree to share their electrons. This sharing creates a really strong link that holds them together as one unit, as a molecule. The key word to remember here is share. On the other hand, you've got ionic bonds. Now this is less of a partnership and more of a giveaway. One atom literally hands over an electron to another one. So the atom that gives the electron away becomes positively charged, and the one that takes it becomes negatively charged. And you know what happens with opposite charges, right? They're powerfully attracted to each other, like little magnets. And as you'd expect, these totally different relationship styles lead to completely different behaviors. Just look at this chart. Covalent substances, the sharers, they tend to have low melting points, and they really don't dissolve well in water. But now check out the ionic substances, the givers and takers. They have super high melting points, they're hard, and, this is the big one for our mystery, they dissolve in water and conduct electricity when they do. Okay, we've got our two big puzzle pieces now, the reactivity ladder and the two types of bonds. I think we're finally ready to go back and solve those mysteries we started with. So, mystery number one. Why does the iron fence rust while the gold ring stays shiny? It is all about their place on that reactivity staircase. Iron is sitting right there in the middle. It's reactive enough that it's more than happy to give up its electrons to the oxygen in the air. But gold? Gold is at the very, very bottom. It's one of those stable elites, holding on to its electrons for dear life and just refusing to react. And what about the salt? Well, table salt is held together by an ionic bond, that give and take relationship. So when you drop it in water, the water molecules literally pull those positive and negative salt ions apart. What you get is this soup of freely floating charged particles, and that is exactly what allows an electrical current to zip right through the water. It's a direct result of that ionic bond. So if there's one thing you take away from all this, let it be this right here. Reactivity, that's the spark. It determines if a chemical reaction is even going to happen. But bonding is the relationship that follows. It determines everything about the new stuff that gets created. You know, these aren't just some abstract rules in a dusty chemistry textbook. They are the fundamental design principles of our entire universe. And by understanding them, we can do incredible things, create life-saving drugs, build stronger and lighter materials for our cars and planes, you name it. Knowing these rules lets us become architects of matter itself. So the only question left is, what amazing things are we going to build next?